Part 1C, permutations with repetitions and restrictions. Okay, so let's do repetitions first. So if you were considering arrangements of items where some of them are identical, it makes sense that there will be fewer possible arrangements because some of the arrangements will be the same. Consider the word pool. We can arrange all of the letters differently like this. Now, look, we've colored the different O's so you can kind of distinguish which one's which. But if you have a look, pool, you can have the orange O first, then the blue O, okay, or the blue O, then the orange O. Really, we can't distinguish them. They still say pool. Okay, and we can do the same. We can have the orange O first, then the blue O, okay, the two P's, then the two O's again, then the L, okay, opal, okay. Anyways, there's two arrangements of each kind here. So there's fewer total arrangements. In general, a set of n objects with A of a kind that are identical, B of a second kind that are identical, and C of a third kind that are identical, and so on, can be arranged in n factorial divided by A times B times C factorials. Okay? The idea is you take the number of items, so the n factorial, and then you divide by the number of repetitions. Okay, so let's try a few of these and hopefully it'll clear that up. Okay, how many different 8-letter arrangements can you make using the letters of aardvark? Okay, so there's 8 letters in there, so that's 8 factorial. Then we have to divide by anything that's identical. Okay, so there's 1, 2, 3 A's. Okay, 1, 2, 3 A's, so we divide by 3 factorial for the A's. Is there anything else that's the same? Oh, look, there's 2 R's. There's an R here and an R there, so then we divide by 2 factorial. Okay, that leaves us with a D, a V, and a K. Those are all different, so this is all we really need. Okay? So 8 factorial over 3 factorial, 2 factorial. Remember, on your calculator, either use the fraction template for the TI Inspire folks, okay, or this bottom part has to be in brackets, okay, in order to make the numbers work out right. So the answer here works out to 3,360 different arrangements of aardvark. Okay. Now, how many different arrangements are there using all the letters of the word Mississippi? Okay, awesome. So let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So it's 11 factorial over. Okay, so there's only one M, so don't have to worry about him. But there's 1, 2, 3, 4 I's, so divide by 4 factorial. There's 1, 2, 3, 4 S's, so divide by another 4 factorial, and there's 2 P's, so divided by 2 factorial. Okay, so 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. So when you type this all in, remember that bottom is either in brackets or you use the fraction template, and you get 34,650 different ways of arranging all those letters. Okay. One of the applications of permutations with repetitions is called pathway problems. Okay. So consider a town with streets and avenues at right angles to each other. How many paths can you follow from one corner of the town to the other, from A to B, if you always move closer to your destination? Okay. Now, I'm just going to draw one of these particular paths for you. And it makes sense that you always have to move closer, because if you go this way, then this way, this way, this way, this way, okay, if you can move backwards, then we could just go and it would take forever, or there'd be an infinite number of different paths. So we always have to go closer to the destination. So that's in orange, that is one possible path you could take from A to B. How we do this is we treat this like a repetition problem. Okay, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different roads that you're going to have to take to get to B. Or 10 different blocks, I guess you could say, or something like that. Okay, now the vertical blocks or the vertical roads, you're going to have to go 1, 2, 3, 4. And the horizontal roads, you're going to go 1, 2, 3, 4, 5, 6. So there's 4 vertical roads, 6 horizontal roads, and there you have it. So you figure that out. It is 210 different ways. Now, on my little path that I made the example for, let's draw in blue. Let's just make sure that works. Okay, we said there was 4 vertical paths. So 1, 2, 3, so 4 vertical paths, and then 1, 2, 3, 4, 5, 6 horizontal paths. So it does work, so all good. Okay, so that's number 2. And then number 3 here, the pathways can get a little more complicated. Okay, and the only ones we have to worry about are guys where there's a perfect corner here. When it's not perfect like that, this doesn't work. So anyways, they are restricted a little bit. So look, what we do is we figure out each grid separately, because you have to go through the first grid and through the second grid, so we can just multiply the two parts separately. Okay, so for the big square, we have 1, 2, 3, 4, 5, 6, 7, 8 different paths. Okay, and there's 4 horizontal ones and 4 vertical ones. Times, okay, now we figure out the rectangle one. There's 1, 2, 3, 4, 5, 6 roads, paths, whatever. Okay, and then there's 4 horizontals and only 2 verticals. Okay, so we take those 2 answers and we multiply them. So this is 70 different paths, and this one is 15 different paths, and then we multiply the 2 together, and we get 1,050 different paths to go from A to B. Okay, great. All right. So now we're on to permutations with constraints. Okay, in these questions, there are added elements to the arrangements. The key here is to read carefully. The blanks of fundamental counting principle can be helpful to make sure all the required elements, or all the required constraints that's supposed to be, are taken into account. Okay, example. How many ways can 1 French poster, 2 math posters, and 3 science posters be arranged in a row on a wall if? Okay, the 2 mathematics posters must be together on the end. Okay, so let's see, you got 1 French, 2 math, and 3 science. That's 6 posters in all. Okay, so we have 1, 2, 3, 4, 5, 6 blanks, and the math posters have to be on the end. So I have 2 choices for this poster and 1 choice for that one. Because once you've picked one math, now we are assuming that these are different math posters. Okay, so that's an assumption we have to make here. Okay, so 2 math posters, then we have 1. They are on the end, and awesome. Okay, so then we have 4 choices here, then 3, then 2, then 1. So really, I can finish off with fundamental counting principle, or I could go, there's 4P4 there. That's the same thing. The second 4, that's how many blanks we take up. So there's 4 things, and I want to permute 4 of them. Now, just for the fun of it, 4P4 is the same as 4 times 3 times 2 times 1. They're exactly the same. So we could use fundamental counting principle, or we could do all permutations, 4p4 times 2p2. Okay, that's the same thing. I really like using either a combination of both or just the blanks because it's very visual. You can really get a feel for what's going on. Okay, now, we should finish that. Okay, so that is 4 factorial times 2 factorial, so that's okay, so that is 48 different ways of arranging these posters if the 2 math posters are on the end. Okay, now letter B. The 3 science posters must be together. Now this one's going to be a little bit tricky. Okay, so I need you to pay attention carefully. So there's 6 blanks. 1, 2, 3, 4, 5, 6. Now, the 3 science posters have to be together so that they make a group. So we're going to separate them off, the 3 science posters, and inside this little group it's 3 times 2 times 1, or 3p3. Now, this question does not say they have to be first. Okay, so this group counts as its own thing, or its own blank. Now, here's why. Okay, because I can have a math poster, then the 3 science posters, then another math poster, then the French poster. Or I can have the math poster, the French poster, then the 3 science posters, okay, then the other math poster. So you can see that there's 4 distinct things that I'm rearranging. Okay? And then inside this little bracket, the science posters can be rearranged as well. So really, this group makes its own blank. So there are 4 ways, 4 choices for what comes first, then 3, then 2, then 1. So this works out to 4 factorial times 3 factorial, right? 4 times 3 times 2 times 1 times 3 times 2 times 1. Okay, if we want to use the permutations, that's 4p4 times 3p3. Again, I really like the blanks because it's extremely visual. So it's 144 ways of doing this. That one's tricky. Okay, now C. What if the 3 science posters can't all be together? Now, this one is hard. There's no mathematical way to straight figure this out. You can figure out when they are together, but you can't figure out when they cannot be together. So the only way to do this, okay, we know from B that there's 144 ways where they are together. Okay, now if there are no restrictions whatsoever, okay, there would be 1, 2, 3, 4, 5, 6. So that would be 6 factorial, or 6p6 ways of arranging them all. Okay, so if we figure that out, 6 factorial, 6p6, that is 720 ways. Okay, so there are 720 different ways of arranging all the posters. In 144 of those, all the science posters are together. Okay, now, in the context of this question, it just says that all the science posters can't be together. It doesn't say that you can't have 2, then say the math poster, then the other science poster. So this particular way of doing things, okay, it allows for 2 of the science posters to be together, but not all 3, which is what the context says, all be together. Okay, so there's 144 ways for all the posters to be together. There's 720 ways for you to arrange them all. So we just take all minus together. Okay, so there's 720 ways. 144 of them have all of the science posters together, which must mean that there's 576 different arrangements where the science posters aren't together. Okay, hopefully that makes sense. It's just, it's a lot of words, so yeah. So all minus the together part. Okay, so 576 ways. Okay, so that is that one. Okay, so now we move on to arrangements requiring cases. There are types of questions where one result impacts another, so things like they both can't happen at the same time. In these cases, we have to separate out the different scenarios and then add the individual results together. So, yeah, that's not a great explanation. So, okay, so example 5, let's see if we can set the stage to make more sense of this. How many 4-digit odd numbers can be made using the digits 1 to 7 if the numbers must be less than 6,000 and no digits are repeated? Okay, no digits are repeated, odd numbers. Okay, so there's 4-digit numbers, so we could start with 4 blanks. Now, what does it mean to be an odd number? Okay, it means that we have to end in an odd number. So if we're using 1 to 7, so that's 1, 2, 3, 4, 5, 6, and 7. Okay, so the odd numbers are 1, 3, 5, and 7. So 1, 3, 5, and 7. Now, you might, using the stuff we've learned before, you might be tempted to put a 4 there because there's 4 choices. Okay, that's great. The problem with that is if there's 4 choices for this one, how many choices do you have for this? See, because this, to be less than 6,000, the first digit has to be 1, 2, 3, 4, or 5. So if you have 4 choices for this last one, what happens if you say pick the 5? Okay, if you pick the 5, then you've only got 4 choices here. But if you pick the 7 for one of these, then you have 5 choices. They both can't happen at the same time. So which is it? Do you have 4 choices for the first or 5 choices for the first? Okay, that's why we have to separate out these choices. Okay, so we're going to separate them out. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so what happens? Okay, so we're going to pick the 7. The 7 is the only one that isn't in both groups. So that's the kind of the linchpin. So if we pick the 7 to be last, okay, so there's one way to pick the 7 last. Okay, then we have all 5 choices here, 1, 2, 3, 4, and 5, to be under 6,000. Okay, so we have all 5 choices. Okay, and then after that, we can pick whatever we want. So we have 1, 2, 3, 4, 5, 6. So there's 7 numbers. 7 numbers. Okay, we picked 2, so we've got 5 left, and then 4 left. So this is how many ways we can have the 7 last. Now, of course, we say the 7 is not last, so not 7. Okay, so that's going to be either the 1, the 3, or the 5. Okay, so there's only 3 choices for this one. Okay, but what that does is it takes either the 1, the 3, or the 5 out of the first selection. So now we've taken one of those numbers away from here, so there's really only 4 numbers to choose for the first number. Okay, right? We can't have 6, we can't have 7, and we've already picked either the 1, the 3, or the 5. Okay, so there's 3 numbers here we can't choose. So there's 4 numbers we can choose. Okay, so we've picked 2 numbers now. Okay, so there's still 5 left, so 5, then 4. And see how we separated out the cases. So we said the first one was 7, or the last digit was 7 in the first scenario, and then it was not 7 in the second. So we can either have the 7 last or the 7 not last. Or, of course, implies addition. Okay, so if we figure out that part, there is 100 ways to have the 7 last, and there are 240 ways, 240 numbers under 6,000 that don't have 7 last. Okay, and then we add them and we get 340 different ways of having digits less than, or numbers less than 6,000 with those digits, odd numbers, digits not repeated. Wow, that's a mess. Okay, let's try another one just to kind of cement it in. So how many even 5-digit numbers are there? Okay, remember that 0, 1, 2, 3, 4. Okay, if you put a 0 first, it doesn't count, right? Because that really is that, and so 0, 1, 2, 3, 4 is 1,234, which is not considered 5 digits. So basically the 0 can't be first. Okay, now what does it mean to be even? Well, even means you have to end in 0, 2, 4, 6, or 8. Okay, awesome. So, oh look, the 0 can't be first, but it might be last. So then again, that's why there's the 2 scenarios here. So we're going to draw blanks. So 5 blanks. Okay, now we're going to draw that twice because there's 2 scenarios. The 0 can be last. Okay, so 0 last, or the 0 not last. Okay, so if the 0 is last, there's one way to do that. Okay, and then there are 9 digits left. So 9, then 8, then 7 times 6. Perfect. Okay, if the 0 is not last, okay, there's 4 ways to do that, right? There's 2, 4, 6, or 8. Remember, to be an even number, we have to end in those. So there's 4 choices. So there's 9 numbers left. But remember, 0 can't be first. So of those 9 numbers, I really only have 8 choices. Okay, awesome. So 9 numbers left, there's 8 choices. So there's 10 digits in all. I have now picked 2 of them. So now there's 8 digits left. No further restrictions. The 0 is back in the pile because we're allowed to pick him now. So then it's 8 choices for this, then 7, then 6. So the 0 being last, if you multiply all those, that's 3,024. Okay, the 0 not being last is 10,752. So remember, this is an OR situation. The 0 is last or the 0 is not last. So that implies the addition, which makes 13,776. Awesome. So there is our final answer. Okay, so I want you guys to practice permutations by completing these questions. So it's section 11.1, page 524. Okay, numbers 1 through 11, 15 through 17, 20, 22C, 24 through 26. Seems like there's quite a bit, but you need to practice these. Okay, so good luck. We'll see you next lesson.